So in tonight's class, we want to introduce the idea of frames. So want to see how you handle frames and also perhaps maybe touch a little bit on machines. Now, one thing I like saying, I don't know if I've mentioned it with you guys or what, because I only have very few jokes and I tend to use them over and over. I remember the first time I saw this word, I was very young. I think it was grade 7 or something. You guys can actually guess how I read this word. It was very funny. If you can guess, just let me know. Send a VN in the group. I'll acknowledge if you pronounce it the way I pronounced it at first or something. I remember it was a class and then you had to. Pardon?
At how much?
At how much? Come on. You guys don't like me that much. You want me to pay you to pronounce it, to laugh at me, to come on. Anyway, so yeah, if you manage, try it out. So yeah, we want to look at frames and machines. So I actually almost went and pronounced it the exact way because that's what is in my head right now. But I want to look at frames and machines. And the focus of our class tonight will basically just be how we draw free body diagrams when it comes to these frames. It's literally the same as what we did under trusses and how we were looking at let's say free body diagrams for those members or those type of supports. But now we want to be able to account for all the forces that are acting um, through a specific member. So here I want to know what would be the forces acting if we were to just isolate this member here, and what would be the free body diagram if we isolated that member, and also if we just got this member. Same thing here, if we just isolated ABC, this member, what would be the forces acting on it? And also if we isolated this, and if we isolated that. So this is what we will be doing here. It's the same thing here. Isolate the members, isolate ABD, isolate CEF. What would be the forces acting through each member? Now, ideally, we'll be calling these as frames. And what a frame is just a member which is under the influence of multiple forces. So these are just going to be multi-force members. So under frames, we'll be discussing structures which are composed of pins, like I think you can tell here, you have a pin here. And then these are pin-connected multi-force members. So they're members which experience multiple forces and they are connected by pins. So this is what we will be analyzing in this topic. You can see it's the same thing here. And what we want to see is how do we first come up with free body diagrams for such structures? And then next up will be how do we actually find forces acting at specific points using the same conditions of equilibrium. So this is what we're going to be looking at. And just as we did in the previous topic, here for the joints, direction of the forces or the reactions there will be assumed. So we'll start by assuming the sense of each force, the direction of each force, and the correct direction.
Sir,
yes, please.
I can't see the screen.
I think it's only you. Try to log out and then come back because I have two devices connected. I'm able to see the screen the other side, so you should be able to see it too. Yeah. Okay, so yeah, basically this is what we're doing. Yeah, so I was saying the direction, just like before, will be assumed, and the correct orientation of a force will only be certain about it when we perform calculations, and then maybe it comes out to be negative, then we know the assumption was wrong, so we'll take the opposite. Now let's start with free body diagrams for such structures. So this is going to be our focus for tonight, free body diagrams. Now, the rules of coming up with free body diagrams here are quite similar to what we did in the previous topic. But here, okay, so is this valid? Okay, yes, it is. Okay, so they are pretty much the same methods that that we used in the previous part. But when it comes to how to determine the forces acting at the joints or maybe the supports for frames or maybe machines, what we must first do is disassemble all the members of that structure. So you first want to disassemble the members. After you disassemble, then draw the free body diagram of each part. So this is the approach that we'll be taking. So in order for us to determine the forces, for example, if we were looking at, we can start with, which one looks more basic? I think these look more basic, perhaps this one here. So if we wanted to come up with a free body diagram, or if we wanted to determine the reaction forces, let's say here, here, and maybe even there, the first step that we'd have to do here is disassemble this structure. By disassemble, or I'm trying to say here is draw these members separately. So we'll draw the member A to B. So we'll draw it on its own. So you're only drawing the outline of the member all the way until it ends. Okay, something else is coming out. Okay, not really working. Try to draw it as something like this. Okay, so this is one part. So this is the member A, B, and then the other side, the other member. Okay, so you dismember or disassemble, not dismember, disassemble all the pieces or all the frames or the members of the structure. So draw them as individual pieces. Now, what this is actually saying, it doesn't mean that if a member, like the way this one is, you see to say this is actually all the way from here up to the very end there. So when drawing this, you don't look at, okay, so since there is a something here, that means that when I am disassembling this, I should only go up to the point B and then end there. This would be wrong. Instead, you have to start from here, going all the way up to the very end there. But you're only looking for the outline when it comes to free body diagrams, so like that, and like this. But of course, we're drawing them separately. So I'll draw this there, and then I'll come to this one here. Like that. So this would be the other part. And then you can see that you have one which is running across both. So I can get this and we can place it somewhere there on its own. So after you're done, so this is the approach you'll be taking literally with all the questions that we have here. You can also show, if you have to, you can also show the supports there, of course. But here what I've done is I just want to focus on the members and we'll show the reactions, how they affect those members. Now, after you're done with that, what comes next? You isolate the members, which is what I was trying to demonstrate, how you isolate the members. After isolating the members, so that is your step one, isolate the members so that you can draw a free body diagram for each member. So once you've isolated them, you now want to get a picture of what your x-axis is. Establish where the correct coordinate system that you're using. For the most part, we'll be taking this to be our y, vertical forces to be in the y, and horizontal forces to be our x, to be in the x. But you want to pay attention to the question because sometimes they'll just flip them. They can put y here, they can put x there. So pay attention if such a coordinate system is specified for you, then you have to follow it. If it is in 3D, of course, you know to say that's a whole different ballgame. Okay, that's step one. So step one, isolate the members. So isolate and draw. Yeah, so isolate each part. Say isolate the parts. Once this is done, you can then identify all the two-force members. Now, what do I mean by two-force members? You want to look for members which are affected or which are experiencing only two forces. Not forces in terms of components, but forces in general. So you want to find or identify the two-force members of any of the system that you've been given. A good example I would give is, take for example, this diagram here. So if you look at this diagram here, and then you wanted to find, or let's say you're going through these steps, and then you want to identify a two-force member. What you have to see is that if you looked at the member BC here, so if you looked at the member BC, you have to observe that it's not a two-force member. So the force BC is not a two-force member. Why? It experiences a force here. It will experience a force at this support. It will also experience a force at the other end. So BC will not qualify as a two-force member. But the member AB, on the other hand, does qualify as a two-force member. But here's what I want you guys to try to justify. We're saying that this one qualifies to be a two-force member. But how come? I'm going to draw this, but I'll just indicate one or two things. And I want you guys to try to justify why this one qualifies to be a two-force member. That's what I want you guys to try to justify. Because if I tried to, let me isolate this. If I tried to look at just that member, what you see is that at this point, you can argue to say that that looks like a pin. So you might say that, okay, for this pin, maybe we're seeing a horizontal force and a vertical force. And if you look at this one here, this looks like a pin at A as well. So you can say that since that is a pin as well, let's place it a little bit down. That is a pin as well. So for this pin, you're perhaps seeing a horizontal force as well and a vertical force. So I can say this is A in X and this is A in Y. And here I can say this is B in Y and this is B in X. But this is a two-force member. But when you count these forces I have indicated here, they are 4. Why is it that then this is a two-force member? What do you guys think? What do you think?
Because okay, it's just a try. You said it's two forces in general and not the component part of the forces.
Yeah.
So it's like we have BX, BY, AY, AX, but we're looking at them in terms of A and B.
Yes. So what you have to see here is that if you combined AX and AY, squared, square root, what this will give you, of course, is just the force A. So the force A, of course, a combination of these, you expect it to be in that direction. And in the same way, if you combined BX and BY, it will give you a force P that will be in that direction. So these now are the two forces that are acting along that member. So when we say two force members, we're looking for members like this one, which will only be under the influence of two forces. So this is what we'll be going for. Okay, so that was a good observation. Okay, so what else? So you see, identifying such members is going to be very helpful in terms of one thing. See, for these members, since we are utilizing equilibrium, what you have to understand is that the only way that this member will be in equilibrium is if A and B are actually equal. but just opposite, as you can see here. So that's the only way that this member will be in equilibrium. So if we can identify members like this one, it makes our work even way easier, so that it reduces the number of equations we have to play around with, or the number of unknowns. Just let's say the number of equations that we have to play with, because such members can actually, they can be omitted. Of course, their effect on the whole system will still remain, as you will see that they will be interacting with the frames where they are, the members where they are connected. So we'll still account for that. But all we're trying to say here is identify them, so that for these, it will be easy for us to just conclude that, oh yeah, A is actually equals to B. Not necessarily equal, we'll say 2 minus B. So that in magnitude, they are the same, but in direction, they're just in opposite directions. So this is a thing that we'll try to use every now and then when we're dealing with two force members. Okay, any questions there? Okay, so with that in mind, let's try to use those 2 points and then see how we can draw these free body diagrams for these questions. And to start with, I want to start with this same question. Okay, so let's start with this same question. And what we want to do here, we want to just understand the diagram, identify the members. And then if you have 2 force members, you want to account for them and then draw the diagram. So how does it go? Okay, so let's start. We'll start by to disassemble the members. So we'll start with the first one. So we have this one here. And then we have the horizontal one, that is BC. Okay, so this is BC, and this is AB. Okay, so we already identified AB as a 2 force member. Having done that, it becomes easy for us to actually evaluate it. So let's account for the forces acting along that member. So here we'll just place this. We are assuming that the force down here will be going in this direction. And of course, if it is going in that direction, then the other one here has to go in the opposite. So when you draw these, label your forces. So I'll label this as the force B. I can say FB. So I can say this is, let's say FAB. Okay, someone trying to join us. Okay. So take that as FAB. Then we know to say that the 2 are equal. They are just opposite in direction. So this will also be given a magnitude FAB. Once this is done, we then move to this member. Now, what is happening to this member? The first thing you want to do is take into account the forces which are applying on this, the external forces. It's easy for you to actually forget them, but you want to account for them just when you start so that you don't even forget them. So we'll place this force. It's exactly halfway since this is 2 and that is 2. So we'll place that force, let's say somewhere here, and it's going downwards. So that is labeled 2,000 newtons. So that has been accounted for. Now we want to look at what is happening at the ends. We're seeing a connection here that is a pin. So that being a pin, we know to say to have those 2 components. But here is what happens here. When you have 2 members connected, perhaps I should have added that among our steps. When you have two members that are connected, so in this case, you have, let me draw them as vertical members. So if let's say I had one member like this, connected to another member like this one. So what you have to see here is that if the forces on the two members can be drawn, if let's say they were to be, if these members were to be drawn separately, let's just color them differently. Okay, so if you have these two members like this, and I was to just draw them separately, and you have this one on top. What you have to see here is that if let's say the forces on the one down were such that this is going down like this, and the other one here is going upwards. What you have to understand is that the same force, if this force is, let's say, FA, this force will actually be the same force that this member will be experiencing, but it will be going downwards. So this is one property that you have to understand. If you have two members that are connected at some point, then the forces that they will exert on each other will literally be equal, but just opposite. So if this is FA, then you have to see that even this one here has to be FA. So this force here is basically the same as this. The difference is in terms of their direction. What am I trying to imply? In this case, you have this member AB connected to this member BC. So what happens is that since I've decided to work with the two member force here, I've labeled it FAB, and that is FAB there. So you have to see that this will actually be, let's just get it from here. This will be attached to somewhere there. And since I've said that from at this pin here, at the pin here, this is where we'll have this force AB acting downwards like that. What it implies is that the member BC will experience the same force, but just in the opposite direction. So for the member BC, it will experience this same force AB, but now this force will just be in the opposite direction, but it has to be in the same axis as this one. So this becomes FAB as well. These are just magnitudes. So once that is done, then we move on to the next part. If you think about it, it's breaking this force AB that actually creates the components that will be acting at that particular point. So let's go to the joint C. Do we have questions before we proceed?
Yes, I do.
Go ahead. Yeah.
If we started by assuming the forces with the second diagram BC, and then for FAB, where there's the force FAB, if we started with that one, we're going to draw it horizontally, meaning even on the first one, it's going to go in horizontally. I can't draw. So
Go through that one more time. Sorry, just go through that. If we started with BC.
My network okay?
Yeah. If we started with BC.
Yes, if we started with B, the force we're going to draw horizontally, right? In the horizontal axis.
Which force is that? The force at B or the force at C?
Both of them. FBC is going to go in through the left side and the right side.
Okay. Yeah, let's.
Right.
It will. We will have. Okay, let me ask it to you like this. I think I do get where you're trying to go there, but let's just make sure you're going in the right direction. If we did start with that one, BC. So the first thing you want to identify is how is BC connected? Let's say at point C. What connection is this? What connection is that? So that's a pin.
Is that one?
That's a pin at C, right? So that
Yes.
being a pin at C, we expect two reactions. You can choose where the reactions must go, to the right or to the left. So we can even say, let's say to the right. So this is going to be, since that's point C, we'll say this is the reaction at C, but in the x-axis. The second reaction, let's take it to be downward. So say this is going to be the reaction at C, let's say in the y-axis. So here we'll have two reactions. It'll be the same thing when we came to the point B. So if you look at the point B here, you see two reactions, you see a pin connection there. So that being a pin connection, what you expect there is that it's going to have those two components as well. So for that pin, you expect that you're going to have two reactions. One reaction will have to be in the x-axis. So say this is B in x. And then the other reaction, you can place it something like this. And this is going to be B in y. Do you get that?
Okay, I think you've even answered my question, yes.
Okay. Okay, so that's okay. So we proceed with this. So at the point C here, we want to also guess what is happening here. Clearly, this is going to have an upward component and a component in that direction. So if we wanted to guess the components at point C, that just make sure that this frame is, or this member is in equilibrium, the x component has to oppose this one, so that the x component at C will be going to the left. So this is going to be Cx. Even if you had to guess it the other way, the math would still show you that it was supposed to go to the left. And then the vertical component here, obviously it has to balance what this one is doing. This one is pushing down, this one is pushing up. To make sure that everything is just in equilibrium, the vertical component here will have to push up. But again, even without trying to reason through, you can just guess their direction and you should still be able to get the correct sense later on. So let me remove these lines I was putting here. And this becomes the free body diagram for our shape. Is that okay? Okay, so yes, when trying to perform calculations, you might then want to express some of these forces in components, as in this one, you might want to express it as a component like that, and a component like this, and then this one, a component like this, and a component like that, because just working with components makes it easy, even when it comes to evaluating moments. But this is the starting point. After doing this, then it's easy for you to actually proceed to everything else. Let's look at another example. Let's pick this one. And let's try to do the same. Let's try to draw a free body diagram for this question. So try to go through the question, understand what is happening here. So for the frame shown in the figure, draw the free body diagram of each member. That's for part A. Then B, the pins at B and A. At B and A. And then C, the two members connected together. Okay, so this is what we're trying to do. How do we approach it? Well, just like before, we're going to follow those same steps. The first thing that we do, we want to draw the members separately. So we're going to isolate the members. Let's draw this one. And let's draw the other member. Okay, so this is done. So in the first part, what are they saying? Each member. So draw a free body diagram for each member. So we have our members here. Let's see what is happening. For the member AB, so this is our member AB, we know to say this is a pin here, and this is another pin connection there. So how are we going to phrase the forces here? Here, what you see here is that you also have this present. That is a moment. So we're going to put a couple moment, that couple moment there. We'll leave it here. Now, let's just add the reactions that are present. At point A, we are seeing a pin connection. So for this pin connection, we know what it does. It creates two reactions. So we can assume that the reactions will be such that one is vertically upwards. It's acting at point A, so we'll label that as AY. And then the other, we'll label it to be AX. Then next up, at point B. At point B again, we are seeing another pin. So because of that, we are also going to put reactions there. And being a pin, we'll put two reactions. So we'll assume there to A, we get something like this. This is going to be, since that is point B, we'll say that is B in Y. And then for this one, we'll guess it to go to the left. B in X. Any questions there? Okay, so that is done. Next up, the member BC. For the member BC, it's similar to the member AB. We're seeing a pin at B and a pin at C. So because of that, we have to make the same assumptions. So here, of course, when it comes to this member, what you have to observe here is that it will experience a force that goes like this. At that point, this is going to be B in X. And the other side, it will experience a force that goes down. Again, this force is coming from the pin. This has to be, no, this can't go up. You can assume it to go in that direction. But notice that in the end, when you add everything up, you will see when we do it to the pin at B, because this is actually asking us to look at the pin at B. You will see that when we look at the pin at B, it only makes sense that if BY here points down, then this side, it has to point up. So here, we'll assume that this is going to go up. And then once that is sorted out, we come to the base here at point C. So for point C, we guess this is going, of course, first we have an applied force there. That's a force P. So the force P here is shown such that it goes downwards. So that is P. And then we come to the reactions at the pin at C. For the pin at C, we have a horizontal force. Again, this we are assuming. This is CX. And next up, we have this one. So we'll assume this is upwards. So this will be CY. Yeah.
They are on B, on top there.
Mm-hmm.
The forces are going in different directions.
Yeah.
Why?
Okay. So consider the members to be connected to each other. Okay, so consider these members to be connected. Here, of course, the connection is such that it kind of forms a V shape. But suppose the force through the member, let's take this to be, I think we'll take some AB, and then this to be BC. I want to put the other forces here, but let's say, suppose the force through the member BC is such that it's dragging the system in this direction. This would imply that this member when drawn on its own, it will have forces which one will go downwards, one will go like this. Now, what does that imply for the other member? So do I want to draw them together? Okay, I can start like this and easily separate them. Okay, now what you should get here is that equilibrium has to be achieved at each point. At any point that you pick, the sum of forces must be 0. When you look at this diagram that we have here, and if you picked this pin here, the pin at B, remember we're analyzing forces, these are the pin forces, reactions from the pin. So when you analyze reactions at this point, it has to be such that when you sum the forces, what you should get should be a 0. Now, yeah, actually, even without making this drawing, you should still be able to understand this. So by summing forces at the point B there, you should get a 0. So in this regard, this actually makes sense, because if you sum forces in the x-axis, what do you get? From here, you get bx going to the left, and from here you get bx going to the right, which gives us 0. And how about here in the y-axis? If you sum them now in the y-axis, you get 0 as well, because it has to obey equilibrium. So from this diagram, you see that by is going down. So you get by going down minus. And from this part, we get by going up. So this is what will give us by. What will imply this has to go up. Do you get that?
Yeah, I get now.
Okay. So it's similar to that part where I said when you have two members that are connected, the forces to the members will be the same. Let's say two members, like the way I drew those which were vertical, the forces to the members ended up being the same, but they just had to be in opposite direction. Okay, that's sorted out.
Also,
Go ahead.
the previous example.
The previous example.
Yes. For the first diagram, why did we not show
Component.
directions of forces? Why did we not draw A, X, and AY? Is it not the pin as well?
Yeah, I think I did mention that. This being a two-member force, we just went straight into doing this. But I think towards the end, I did point out to say that when performing calculations, you still can express these forces in components. It's the same components from the pins which actually create the forces I've labeled as FAB. Even here, you can still do the same. You can still do this, and you can do that. Do you get that? Yeah.
Yes. Okay.
Okay. Okay, now look at the second, look at part B of our question. Part B actually now gets to the question that I was asked earlier on, where now we're saying, why is this one going to point upwards? It will make sense when you look at part B. Let's draw a free body diagram for the forces acting on the pins B and A. Let's look at B. B is actually what is even more interesting. When you look at B now, that pin, observe that if I was to draw the pin to be big enough, something like this, the pin will actually experience only two forces. The two forces, one will be a result of the member AB, and based on how we drew this one here, the force along that or from that will be going something like this. And the force down here, of course, will be going something like this. But we're only interested in the pin here. So we'll stick to that. So this is going to be the force acting onto the member, or the force to the member. Now, same thing to the force here at for this member, this is BC now. You have to see that for the force for the member BC, based on the arrows that we picked to say this is going like this and this is going up like this, it implies that the force to this member has to be a combination of these two. The resultant of these two is what actually has to give, what has to make way. So we can perhaps draw it as something like this, perhaps. Yeah, something like that. But doesn't really look too nice. But anyway, who says it has to be nice? Okay, so what is happening? I don't really want to look at this one. Let me use this one here. The force through this member comes to be something like this. But viewed from the pin now, if I was to put this member here, now let's view the member from the pin. Now what happens is that you now view these two as if they are connected, and if the member has a force that is going like this, what happens? Then the pin has to experience the same force, but in the opposite direction. I hope you guys got that. If this member experiences a force that goes down like this, then the pin has to experience the same force, but just in opposite direction. In other words, when we looked at the member had two components, and the components were such that one was going down, one was going to the left. So if I was to put the pin now here, the forces through the pin now will be the one to the left will now be swapped onto the pin. It now has to be to the right. BX. This is how the pin will feel that force. And the one going down to the pin, that will actually now be going up. This is if you are looking at the pin. It's the same thing even when it comes to this one here. For the member BC and how it interacts with the pin there, the member BC, we showed that it had two components, one vertical, the other one horizontal. The vertical one pointed up and it was labeled BY. To the pin, that force will now have to go down. And we'll label it BY as well, the same label as this one here. The horizontal one was going to the right. So to the pin, it will go to the left. So again, that was BX. So label it like this. And this now is where everything adds up, because all those forces by the end of the day, they are being felt by the pin. So if I was to get that pin and said, let's deal with equilibrium for our pin, observe that now it obeys the equilibrium condition. For this one now, if you try to sum forces in the x-axis or in the y-axis, clearly you will see that you get zeros. Is that okay?